Download this code from codegive.com, link in the description below. OK, let's dive into the world of deadlock avoidance in operating systems, focusing on the banker's algorithm. I'll explain the concepts in a way that's easy to understand, using a mix of Urdu/Hindi terms where appropriate to make it relatable. I'll then provide a C++ code example to illustrate the algorithm in action. Deadlock avoidance, a detailed explanation. Deadlock bachna, avoidance, is a strategy in operating systems used to prevent deadlocks from occurring in the first place. Unlike deadlock prevention, which imposes very strict constraints on how resources are requested, avoidance aims to be more flexible. The key idea is that the system needs to have extra jankari, information, about future resource requests. With this information, it can make decisions about whether to grant a request, ensuring that granting it won't lead to a deadlock. Contrast with deadlock prevention. Deadlock prevention *60 se rules lagu karta hai, strictly enforces rules. It prevents one or more of the four necessary conditions for deadlock from occurring: mutual exclusion, hold and wait, no preemption, circular wait. This often leads to inefficient resource utilization. Deadlock avoidance *sock samaj kar kam karta hai, acts thoughtfully. It allows the necessary conditions to exist but makes sure that the system remains in a safe state. The concept of safe state. The sabse zaruri, most important, concept in deadlock avoidance is the safe state. Safe state *A system is in a safe state if there exists a sequence of processes P1, P2, Pn such that, for each pi, the resources that pi can still request can be satisfied by the currently available resources plus the resources held by all the preceding processes, P1, P2, Pi1. In simpler terms, a safe state means that even if all processes suddenly request their maximum required resources, we can still find an order in which to grant resources to each process, allowing them to finish and release their resources, preventing a deadlock. Unsafe state if no such sequence exists, the system is in an unsafe state. An unsafe state doesn't guarantee a deadlock, but it means there's a risk of one happening. Deadlock avoidance algorithms aim to keep the system in a safe state. The banker's algorithm. The banker's algorithm, developed by Dijkstra, is a mashhoor, famous, algorithm for deadlock avoidance. It's named after the way a banker manages loans to ensure that they can always honor their commitments. Data structures used in the banker's algorithm. Let's say we have n processes, P1, P2, Pn, and m resource types, R1, R2, Rm. The banker's algorithm uses the following data structures. 1 max nm * a matrix that defines the maximum demand of each process for each resource type. Max ij represents the maximum number of instances of resource type rj that process pi might request. Har process key sabs zayat among. 2 allocation nm * a matrix that defines the number of resources of each type currently allocated to each process. Allocation ij represents the number of instances of resource type rj currently allocated to process pi. Har process ko kitna mila hua hai. 3 need nm * a matrix that defines the remaining resource need of each process. It is calculated as need ij equals max ij, allocation ij. Har process ko kitni or zarurat hai. 4 available m * a vector that defines the number of available instances of each resource type. Available j represents the number of instances of resource type rj that are currently available. Kitna baki hai. The algorithm steps. 1 Initialization *. Initialize the max, allocation, and available arrays with the system's information. Asterisk calculate the need matrix using the formula, need equals max, allocation. 2 resource request algorithm, request underscore resources, process pi, request. A check if the request is valid asterisk. Asterisk if request j need ij for any resource type j, then the process is requesting more resources than its maximum declared need. This is an error. Agar mangziata hi zarurat se, to error. Asterisk if request j available j for any resource type j, then the resources are not currently available. The process must wait. Agar resources available nahi hi, to wait. B. Simulate the resource allocation asterisk. Asterisk temporarily assume that the request is granted. Update the data structures as follows. Allocate karo or dekhan kia hoda hi. C. Check if the resulting state is safe asterisk call the is underscore safe function to determine if the system is in a safe state after the simulated allocation. Asterisk if is underscore safe, returns true, then the request is granted permanently. Agar safe hi to, theek hi. Asterisk if is underscore safe, returns false, then the request is denied. Restore the original values of available, allocation, and need. The process must wait. Agar safe nahi hi, to request cancel karo. 3 is underscore safe, function, safety algorithm. This function checks if the system is in a safe state. A. Initialization asterisk. Asterisk create a work vector of size m and initialize it to available. Work equals available. Work, available resources key copy. Asterisk create a finish vector of size n and initialize all elements to false. Finish I equals false for all processes pi. Finish, har process k like kia wo pura ho gaya hi. B. Find a process that can finish asterisk. Asterisk find an index I such that. Asterisk finish I equals false, process pi hasn't finished. Asterisk need ij equals work j for all resource types j, process pi's remaining need can be satisfied by the available resources in work. Asterisk if no such I is found, go to step, E. C. Simulate the process finishing asterisk. Asterisk if such an I is found, do the following. Resources release karo, or process ko finish mark karo. D. Repeat step, B. Go back to step, B, to find another process that can finish. E. Check if all processes finished asterisk. Asterisk if finish I equals true for all I, then the system is in a safe state. Return true. Asterisk otherwise, the system is in an unsafe state. Return false. Code example, C++. How to run the code asterisk. 1. Save asterisk save the code as a .cpp file, example bankers underscore algorithm.cpp. 2. Compile asterisk compile the code using a C++ compiler, like G++. 3. Run asterisk execute the compiled program. 4. Input asterisk the program will prompt you to enter the number of processes, the number of resource types, the max matrix, the allocation matrix, and the available vector. Enter the values accordingly. Finally, it will ask for a resource request from a specific process. Example input and output. Let's assume the following scenario, from Tannenbaum's Operating Systems, 3rd edition. Asterisk processes, N5. Asterisk resource types, M3, A, B, C. Asterisk max matrix asterisk. Asterisk allocation matrix asterisk. Asterisk available vector asterisk. Asterisk request asterisk process 1 requests, 1, 0, 2. Input to the program asterisk. Possible output asterisk. Explanation of the output. In this case, the request for 1, 0, 2 by process 1 is granted because the is_safe function determines that the system will remain in a safe state after the allocation. Key takeaways. Deadlock avoidance uses extra information to make informed decisions about resource allocation. The banker's algorithm is a widely used algorithm for deadlock avoidance. The concept of a safe state is crucial for understanding deadlock avoidance. The is_safe function checks if a system state is safe by finding a sequence in which all processes can finish. The banker's algorithm can be resource intensive due to the overhead of checking for safe states, especially when dealing with a large number of processes and resource types. Limitations and considerations. Future resource needs. The banker's algorithm requires processes to declare their maximum resource needs in advance. This can be difficult or impossible in some real-world scenarios where processes may not know their exact resource requirements beforehand. Peli se batayo ki kitna chahi. Static resource allocation. The algorithm assumes that the number of processes is fixed. Overhead. Checking for a safe state can be computationally expensive, especially when the number of processes and resources is large. Zayada calculation. Resource wastage. To ensure safety, the algorithm might deny some resource requests that could have been granted without causing a deadlock, leading to some resource wastage. Resource waste ho sakta hai. Conclusion. Deadlock avoidance, specifically using the banker's algorithm, is a powerful technique for preventing deadlocks in operating systems. It strikes a balance between strict prevention methods and the potential chaos of deadlock detection and recovery. Understanding the concepts of safe states and the algorithm's logic is essential for designing and managing systems that need to avoid deadlocks while maintaining reasonable resource utilization. Deadlock se bakni katarika, likan karka bihai. Remember to consider the limitations and trade-offs when deciding whether to implement deadlock avoidance in your system. Good luck.